I'd like to say that at this stage that we do acknowledge that we're coming to you from the traditional homelands of the Musqueam, Squamish, and Tsleil-Waututh nations. And we're very happy that we're able to share the nature with all of these nations. And I think this is especially true for our speaker, whom I'm about to introduce. He lives with a vantage point on the Salish Sea, and it's at the ancestral territories of the Squamish and the Akatlasam Howe Sound Biosphere Region. This region has been very important to Bob over the last number of decades, 3 decades, because Bowen Island has been his home. By training, Bob is a field geologist. He studied at Queen's, and then he did his master's and his PhD at Stanford University. Since then, he's been working he started working, I think, out of Vancouver for the Geological Survey of Canada. He's been a research scientist for 20 years, and by instinct is an educator and an artist. So tonight, I'm so happy to introduce Bob to talk about the geology of Garibaldi area. Thanks, Bob.
Well, thank you, Donna. I'm excited about the talk tonight. It's titled When Mountains Talk. And the reason for that title is that the reason for the title of the talk, When Mountains Talk, is that what I'm hoping to do tonight is promote in you a conversation with the earth. And that's because the earth has a language, and geology really is our collective human effort to understand that earth's language. And the earth writes its stories in rock and soil, in landscapes. And that's what really tonight is. It's a peeling away of some of the stories that are written in rock, soil, and landscapes in the Garibaldi area. As Donna mentioned, I was for a long time with the Geological Survey of Canada. I started off as a research scientist, but I shifted over with time into public education because I just felt as an agency and as a community, geology had so much to tell the general public, and I didn't think we were doing a particularly good job at it. So I jumped in and over a number of years worked with people, including John Clegg, to sort of write books and pamphlets and create maps that sort of told those stories. Oops. Boy, I'm having trouble with my advance, and I don't know why that is. Okay.
Here we are.
Well, good. Glad you're still there. So I retired in 2014, and I discovered making movies. And for the past decade, I've been making movies, over 50 of them, for my YouTube channel, and really telling stories of everything from salmon to herring, to humpback whales and everything else that sort of lives in the Howe Sound area. And more recently, I've stretched out into the Salish Sea in general. And most recently, in the last year, I've returned to my geological roots, and I've done 3 movies on specific geologic features. The first being this curious flat top mountain in Garibaldi, the Table. I'll talk more about that later. The geologic origins of Garibaldi Lake, and also the giant granite monolith that rises above Squamish, Stawamus Chief. And so that's sort of the background for the story of tonight. I want to talk about Garibaldi Park, which is a huge park that stretches from Highway 99 in the west over to the Lillooet River Valley and almost from Pemberton to Squamish. But the talk for tonight is specifically about the most visited area in the park, Garibaldi Lake, access through the Rubble Creek access or the Cheakamus Lake access. So that's really the story place for tonight. Now, Garibaldi takes its name from the mountain. The mountain itself is the original name is Inchkai. It's a sacred mountain to the Squamish peoples. It is in their stories of the Great Flood, the refuge where they tied their canoes to hold them fast to their land. It is also being a source of materials for cutting tools, the obsidians that are on the mountain, as well as ochres, which are important for pigments as painting or for other craft. The park itself has a long and storied history. I'm sure many of you have heard those stories, have been part of them. I heard from Laura that her dad was the first park ranger in Garibaldi Park, and her mom and dad spent the summer of 1951 up there in Taylor Meadow. So that's just I love hearing those stories. Today, it's a busy place, four seasons. There are people pretty much everywhere and all the time. And so it certainly is one of BC's most famous and and loved parks. Now, I want to pay homage now to, I guess, my geological hero, and that is Dr. Bill Matthews. And this is a photo of Bill when he was a young guy doing his PhD research up in Garibaldi. And Bill spent a number of summers up there researching. He ended up writing a whole series of papers about what he sort of discovered. What I love about Bill, he was sort of an old style geoscientist in the sense that his interests were eclectic, and he essentially researched scientifically everything from volcanoes to glaciers to the lake itself. And in a sense, he was sort of geology that is all about one place and just figuring out all the aspects of it. And he's left a wonderful legacy for people like myself because there is this whole science storytelling, which he created. And he was very interested in public education too, and wrote the book on the right there, Garibaldi Geology, as a popular guide. But anyways, I will refer to him through the talk because so much of what I'm telling you, really, he first discovered. So what do I want to do today? I want to take you on a hike. And I'm sure many of you have done this hike, but it is a hike from Rubble Creek parking lot, pretty much the number one trailhead into the Garibaldi country. And then we're going to work our way up through four stops. We're going to, the parking lot actually is a stop, so is the barrier viewpoint that is about 3/4 of the way into the lake, then the campground on the lake, and finally up onto Panorama Ridge. And much of the storytelling will be from Panorama Ridge because, from my point of view, it probably, I'm doubting there's another place in British Columbia where there are more interesting and diverse geological stories to be witnessed than from the top of Panorama Ridge. It's just a gold mine of stories. So we're going to head there and we're going to survey the scene and talk stories. But the first stop is Rubble Creek Trailhead. And the Rubble Creek Trailhead is, oh, I don't know, 5 or 6 kilometers in from Highway 99. When you're going north to Whistler, it's just before the Daisy Lake Dam, which is quite a prominent feature from the highway. Anyways, one of the things that is, whoops. Okay, I just got frozen again. Is One of the things that you see in the parking lot is a sign, and it essentially warns you against overnight camping in the park because of slide hazard. And so, of course, the question is, well, what's the slide? What's the landslide? And the answer to that is you're standing on it. And the source of the slide, as you might guess, and is pointed out by the sign, is this thing way up the valley called the barrier. And it is a raw face of lavas that essentially form a termination to the valley. It's quite odd. The valley is quite defined. It goes up and boom, it runs into this well-named wall of lava called the barrier. And that was the source of the landslide you're standing on. And the landslide looked a lot like this photo here, which is a photo of the Mount Meager landslide back in 2010. And if we were, say, out on the highway looking up Rubble Creek, this is sort of the view you're looking at. This is likely similar to the view that James Downey had in 1857 when he was working his way up the Squamish Valley with the intention of pioneering a cattle route to the interior. And he came upon what he described as a giant lagoon, a tract of overflowed land, and he assumed some lake had broken away in the mountains and swept down. Anyways, it was a big and very impressive landslide that covered 6 or 7 square miles by his estimation. And if we go up in space and we are sort of flying above the Highway 99 and we're looking east here towards across Highway 99 corridor in the Cheakamus Valley, and we're looking across the landslide area to the barrier and then to Garibaldi Lake. And what I've color coded on here is the area of the landslide. You can see it started at the barrier and it sluiced down the Rubble Creek Valley and out into the Cheakamus River Valley into what is now Daisy Lake. The foundations of the Daisy Lake Dam were built on this landslide. And then interestingly, the landslide remobilized. It clearly failed as a series of debris flows, likely driven by overtopping of the landslide dam by the Cheakamus River. And a huge amount of sediment flushed downstream for about 5 kilometers. And you know you're on it when you're driving the Highway 99 because it's dead. It's a very evenly sloped surface, very flat, gently rising to the north. And there's really no other stretch of highway north of Squamish that is anything like it. Otherwise, the highway is quite rolly and wiggly. And here, the surface of the valley has been filled with a landslide, and the highway has this constant grade. Now, if we were to just go a little to the right in this photograph into those trees over to the Cheakamus River, what we'd see is, oops, no, that was over to the Cheakamus River. The river cut exposes underneath the surface that the highway's on. And now we're looking at the landslide debris from the 1856 landslide. Here's a really interesting feature that when you look at it, you go, I have no idea what I'm looking at. And we're at the Cheakamus River. We're looking east up to where the confluence of Rubble Creek comes in and meets the Cheakamus River. And then there's a little peak of Highway 99. And then in the background, we can see the barrier. And out of the Cheakamus River are all these posts. And they sort of have the look of, I don't know, some derelict pier that was, constructed across the river. In fact, what they are is stems of trees that are essentially have been buried and are sticking out of soil that the river flows over. And I sort of refer to them as a ghost forest. And if we're down on the river bar looking across, we can see that there's a modern forest floor with trees growing from it, but there's also a buried forest floor from which these trees are rooted into, submerged underneath the river. And here's a little series of three little diagrams that try to explain how this ghost forest came to be. So the first little sketch here is a cross section of the Cheakamus River valley floor about before 1856. And it's, a bunch of trees as you'd expect on a floodplain beside the river. Suddenly, the landslide happens, but here's the important detail. The landslide happens upstream from where we're drawing this picture. It mows down all the trees in its way as it sort of comes down into the Cheakamus Valley. However, downstream, this resedimented material, this remobilized material from the landslide, essentially moves down in a slow slurry in a way that doesn't topple the trees. It just buries the forest. It buries the whole forest floor and the trees with meters of material. And today, this is sort of the third stage. The Cheakamus River has cut down through this landslide debris, and it's exhumed some of these still standing forest stems, creating this ghost forest. It's just a really interesting piece of geological detective work that people have done. Okie doke. Well, let's head up the hill. This is the tough part of the trail. It's about 900 meters vertical elevation gain to the lake and about 9 kilometers horizontal. And the barrier viewpoint is just at the point where the tough stuff's behind you and the trail is starting to level out. And what you see when you walk out onto a little viewpoint is a close-up of the barrier and this great wall of lava with this sort of rusty cap and then this solid face of lava rock. And what you're looking at is the exposed cross-section through a series of lava flows. And part of the mountain, of course, has fallen away and is now down in the Cheakamus Valley. But if we sort of pivot ourselves a bit to look from the barrier down the valley of Rebel Creek, and we listen, we don't have to listen hard because it's quite loud. What we hear is the flowing water of Rebel Creek. And if we look up in the upper right corner, I've sort of highlighted what you see, and that is Rebel Creek just erupting in this giant springs. It's got to be one of the biggest in British Columbia. And the creek erupts as this crystal clear, really gorgeous water, essentially from nowhere. Well, okay, what's going on? And what it is, this is a very much a cartoon. It's not to scale. It's really just intended to illustrate that water from Garibaldi Lake is percolating down into a big pile of lava flows that have been deposited on older rock and that make up the barrier itself and create a dam that holds in Garibaldi Lake. But it's a leaky dam. And the groundwater sort of flows. Largely, it appears right along the base of the lava flows at the top of the older rock and erupts down as springs in Rebel Creek. Now, while we're on the subject of the lava dam, let's just touch on one other point that always comes up, and that is, will this lava dam collapse in some catastrophic event that would allow Garibaldi Lake to essentially empty in a flood in a hellacious flood would head down the Cheakamus River and into Squamish. And I'm not an engineer. I'm not going to talk about probabilities and likelihoods. But I think one thing that's important to remember is that this lava dam, this pile of lava flows, is over a mile and a half, sorry, a kilometer and a half wide. So that is a huge amount of lava dam. And since the end of the Ice Age, only a small portion of those lava flows have collapsed into Rubble Creek. So there certainly in the future could be a potential collapse that off the barrier I've sort of sketched in just in an artistic way how that might manifest itself. If it did happen to drain tiny little barrier lake, that would mobilize material and could sort of create more of a slurry that would continue down valley further. But essentially, that is the type of hazard that potentially exists. And it certainly strikes me that the idea that the entire lava flow dam collapses seems to be a stretch. Okay, let's keep on trucking up to the campground. And I know many of you have sort of come out on the scene. It's always super welcome because you're pooped if you're anything like me, and you're really eager to just sort of sit and gaze at a beautiful lake, which it is. It's a lake that always sort of takes my breath away. The color of the turquoise waters, the brilliant glaciers that cap this sort of gray granite skyline, bookended by sort of lower forested slopes. The whole thing is really quite fantastic. But, in the spirit of telling stories, we have to acknowledge it's an odd lake, and it's odd for two reasons. For such a large lake, it is at a very high elevation compared to other lakes in British Columbia. And secondly, it is very deep, 270 meters deep. That is deeper than most of Howe Sound, which is a glacier-carved fjord of the ocean. So it's a deep lake. Anyways, we'll come back to that story later. The other thing that's odd is as you walk the shoreline, all the rocks look the same. Very odd. My experience on lakes all around British Columbia is that the shoreline is a mix usually of diverse pebbles. And that's because just about all of British Columbia, certainly at this elevation, was glaciated by Ice Age glaciers. And they left behind a carpet of mixed stuff that they'd picked up from here, there, and everywhere, and they just drop it willy-nilly. And so you usually have quite a diversity of pebbles. Not here. It's all the same rock, which tells me two things. One is something suspicious. Secondly, this particular piece of geography was never glaciated. Which at this elevation, that's odd. And the reason for that is that it is we're standing on a lava flow. And you can tell that by the lava rock that is in your hand. And lava rock can be brick colored, brown, gray, black, but it always has a characteristic feature, and that is that it has these floating crystals of white feldspar in a fine-grained matrix. And whether the matrix is gray colored or black or brick colored, it's a signature that you're looking at volcanic rock. So I make my way in behind the campground and get up onto something that at first blush, boy, sure looks like a landslide. But it's all volcanic rock, and there's really nowhere for it to have come from. What am I standing on? In fact, I'm standing on top of a lava flow, and this broken rock is something that the lava flow produced itself. And here's the interpretation. There's a little picture of me standing up there on these lava blocks, looking puzzled. And this is a cross section through the earth, very much a cartoon. But I am standing on top of a lava flow, and the lava flow has a carapace, an outer skin of this rock rubble. And the reason for that is that when the lava flow was active, um, and had a molten core, its surface was cooling and turning to rock. But as the lava advanced and changed shape, it broke up this rock carapace into the lava blocks that we see today. Okay, well, we've had a little bit of a rest breather. We will now keep hiking, and I'm looking across the lake from the campground now up to Panorama Ridge Viewpoint, which is where we're heading to now. And the next part of the hike, as many of you know, really features the glory of subalpine meadowlands. And you're in meadows, you're moving through small pocket forests, and here's a viewpoint at one of the high points where we can look ahead, look across this beautiful subalpine meadowlands to the trail that we are going to be on. And what's marked in yellow is the final part of the trail that takes us to Panorama Ridge Viewpoint. So, but what I want to do is jump ahead. Well, just a second here. Okay, here we go. And I want to jump ahead to that red dot over on the left, which is the location of the next photo I'm going to take. So we're going to keep walking the trail. We're going to go off the screen, and then we're going to come back on the last part of the trail. And now we're going to jump over to that. And here we are on this ridge ascending up to Panorama Ridge. The last photo was taken back there, sort of on the lower slopes of Black Tusk. And we see two different worlds. One, this subalpine meadowlands that we have been gloriously walking through. However, almost in sort of a split screen to the east is this stony barrens. There's not a tree growing, nor is there a bit of meadowlands to be seen. What's going on? Well, let's sort of move ourselves over to Black Tusk and look back at this area. And this is what we would see. Now, we're standing here over on the right where the arrow points to sort of the Panorama Ridge Trail heading off the right side of the screen. And we're looking out into sort of the landscape that Helm Glacier now is sort of a centerpiece of. And this happens to be about 10 years ago. I'm putting a date up there, 2014. Now we're going to jump back 100 years to the view from about the same position, taken by a photographer in 1920. And the arrow again points to that same place. And what you can see is that Helm Glacier filled a vast expanse of this whole bowl. In fact, the entire Stony Barrens that we were remarking on is in fact recently deglaciated land with the retreat of the Helm Glacier. And so this is a little bit of a shifted view. We're now looking again at sort of the modern landscape with the dashed extent of the Helm Glacier back in 1920. It's a remarkable shift. And if we move back to where we were on the trail, again, looking at that split world, we can see that the Helm Glacier completely covers that Stony Barrens, and at least in 1920 had not made incursions into the meadowlands. And in fact, the Helm Glacier did not advance much further than it was in 1920. And here's some old photos just to remind you what a sort of a different landscape the 1920s were. And so what I'd like to do now, just quickly dip into a couple of graphs. Not everybody's a graph person, but I just want to sort of set a context for what is happening. And I'm going to do that with this graph that essentially is temperature on the vertical axis and time on the horizontal axis. And this graph goes from essentially the year 0 AD all the way to the present. And what it charts is global temperatures over time over those 2,000 years. And you can see sort of the red squiggles, that's just as the variation. But you can see that for, the first 1,300 years, it's relatively flat. And then the temperatures start to decrease, and they do so from about 1300 until about 1850. And then there is a dramatic rise in temperature. And we all know that story. That's essentially the human fingerprint on global climate. But the important point here is that prior to the rapid retreat, which is the story we see, there was a sustained multi-century advance of glaciers that created something scientists call the Little Ice Age. And the Little Ice Age created the maximum glacier advance for the entire period since the last ice age. So the maximum glacier advance occurred literally only 200 years ago, relative to all the time, all the way back 10,000, 11,000, 12,000 years to the end of the Ice Age. So that's a remarkable point. In other words, not only are the glaciers retreating fast right now with the warming climate, but they were at their maximum just in 1850. And this is a second diagram, basically still doing the same thing. Temperature higher on the graph is warmer, lower on the graph is colder. But now we go back essentially over 20,000 years, where we see sort of the role of the Ice Age that is charted by this slowly warming curve from 20,000 years BC to right up to about 12,000 years BC, at which point the temperature stabilizes, a period that geologists have called the Holocene, as opposed to the Pleistocene. Now we're in the Holocene, and this is this post-Ice Age world where temperature was, by and large, pretty stable. But there's a wrinkle here, and that is that in the last 5,000 years, we have seen a global cooling over this period of time. And the punctuation point on that global cooling was the Little Ice Age, the most recent part of that, just prior to this big anthropogenic human-induced warming that scientists, or some scientists, are now suggesting should be termed its own era of geologic time, that being the Anthropocene. So anyways, all of that to say that the tremendous glacier retreat that we're witnessing in Garibaldi is greatly accentuated because just before the retreat started, we had the maximum glacial advance. So the change is dramatic. Okay, well, we're only a couple hundred feet from the top of Panorama Ridge, so let's get up there, which is our sort of fourth viewpoint, and one that I'd said recently has more geological stories, I think, than probably any other place in British Columbia, or at least as good. So we're sort of glorying in the stories, and I'm going to start the first story. There's so many places to go, but let's just start with maybe the most obvious thing is why the heck is the lake so blue? So turquoise in particular. And the reason for that, and I'm sure many of you know this, is that the lake receives glacial meltwaters from both the Sphinx and the Sentinel glaciers, and those glacial meltwaters are full of something called glacial flour, which is very, very finely ground up rock. And it's freshly ground, sort of like freshly ground pepper matters. Freshly ground rock matters too. That means it hasn't weathered and converted from the minerals that the rock formed into some type of clay mineral. And so that those fresh micro things, silt size, clay size, have these very reflective surfaces. And when the multispectral sunlight hits the water, two ends of the spectrum are preferentially absorbed. The particles themselves, this fine glacier flour, and over in the upper right is just a sort of a relative comparison between a sand grain, a silt grain, and a clay grain, just to remind you that the clay and silt are very, very fine, and so they can hang in suspension in water for a long, long time. Anyways, the sun hits this glacial flour rich water. The particles themselves absorb the high frequency purple indigo end of the spectrum, and the water itself absorbs a different spectral area, the red, orange, and yellow spectra. The glacial flour basically scatters back to our eyes then just the blues and greens, which collectively blue and green gives that sort of turquoise color. Okay, story two, let's keep going. Over to the left is a really interesting looking valley, and it is the Sphinx Valley. And so let's just head over there with a telephoto lens to examine some interesting stuff that documents glacial retreat. And here's a photograph taken from Panorama Ridge in 1928 and then again in 2025. And what you can see is the same story as the Helm Glacier, a tremendous retreat of the Sphinx Glacier to its present position. And the red arrow just identifies the UBC Burton Hut, which is a well-known feature in the Sphinx Glacier Valley. And here we're zooming a little in on that, and I've just drawn the extent of that 1928 photo documenting the extent of the glacier. And you can see that most of the valley now has been deglaciated. The glaciers are really in fast retreat. And what's left behind is basically glacial debris and bare sculpted rock. Now, what I'm like to focus on is that area that is beyond the extent of the glacier, because the question is, okay, a photograph of 1928 just nails exactly where the glaciers extended to. But can we learn anything about advances that would have been perhaps prior to 1928 and pushed the glacier further? And in fact, we can. And here we're down in the valley now, and there's Burton Hut in the foreground. Sort of the base camp for UBC adventuring mostly in the winter, the snow touring up into the high winter snowfields. And you can see the extent of the glacier back in 1928 and a very sort of robust regrowth of vegetation that is at least older than 1928 because the glacier wasn't here at that in 1928. So that sort of buckbrush has grown up, much to the bane of people who want to try and get through it. It can be really nasty stuff. but right at the lake's edge, and the location of where that photograph was just taken of Burton Hut, is this debris ridge of glacial debris. And it forms the shoreline at this point of the lakeshore. And I want to examine this because geologists and John Clegg and his students have been the ones that have done this work because they've been able to date the age of these debris ridges. And, oops. So this diagram is just a cartoon describing how these debris ridges, which are called moraines, form. And they can form by essentially the glacier acting as a bulldozer and pushing stuff in front of it, but they can form in a second way, and that is when the glacier, which acts as a conveyor belt, it is always flowing downhill. The ice and debris in it is always flowing downhill, whether or not the snout is advancing or stationary or retreating, because the position of the snout is a balancing act between the glacial flow downhill and the rate of melting of the snout. And there are times when those two balance for extended periods of time. And because of that, you have a fixed snout that's acting as a conveyor that just keeps dumping stuff out of the end of the snout, building a ridge. And that's exactly what's happened here at in this Sphinx Valley. Now we're sort of up in the air. This is a photograph from research by John Clegg's group. And here they're just putting white dots on these concentric set of ridges that they've been able to date as snouts of the glacier based on vegetation, woody material that has been overrun by or buried into these ridges and are dated by radiocarbon dating. And you can see that they've been able to get dates as far back as 1690s for the advance of for the snout of the glacier. And you can see that 1690s one, which is way over on the right-hand side of the photograph, would extend offshore and pretty much requires that the snout at that time was partly floating in Garibaldi Lake. So imagine Garibaldi Lake with calving icebergs in it. Okay, let's come back from Sphinx Valley. We're back on the ridge and we're asking another question, sort of puzzled by the question of why is Panorama Ridge, this rounded top ridge, so different from the ragged peaks in the background? And, you know, personally, I'm thankful it is. It's an easy walking ridge. It allows you to maneuver around, you know, big chunks of Garibaldi in a way that I, not being a climber, can't do on the rugged terrain of the back peaks. The reason why there is this difference is a difference in the materials that make up each. Those mountains in the background are granite. The Panorama Ridge is underlain by sedimentary rock. And here's a photograph of some of that sedimentary rock on the ridge. And what you're looking at are tilted layers of sandstone. Those are the white layers, separated by mudstone layers, which are the dark layers. And so you're looking at an ancient set of seafloor deposits that have been turned to stone and tilted in some type of deformation event, something that tilted the beds. And if we were to cut a cross section through the earth to examine the types of rocks that are below us, what we would find, first of all, let's just get our geography straight. So this is a cartoon cross section. On the right is the Cheakamus Valley, or sorry, on the left, Cheakamus Valley with Highway 99 in it. And we go up and over Black Tusk, and then there's this sort of gentle bump of Panorama Ridge where we are right now. then there's the lake, and then the high peaks of Castle Towers. And the geological materials, simply stated, are granite for Castle Towers, but interestingly, that granite extends all the way underneath the Garibaldi area and shows up again in the valley of the Cheakamus River. On top of that granite has been laid down these sedimentary rocks shown in green. And then younger still are the volcanic rocks of the Black Tusk and other volcanoes, which have been deposited on top of the sedimentary rocks. So that's the holy trinity of Garibaldi Park, essentially granite, sedimentary rocks, and volcanic rocks. And each rock type has its own unique landscape forming characteristics. Hard granite with the craggy peaks, soft sedimentary rocks create these soft ridges, which provide so much access in the Garibaldi area. You know, when you think about what is it that makes Garibaldi so popular, and obviously the lake is a key feature, but what creates the access are essentially soft ridges that allow a hiker to navigate large pieces of turf, as well as the soft valleys in between. And here's a photograph of some of those sedimentary rocks over on Gentian Ridge, and you can see the layering of the sedimentary rocks in the mountain, sweeping along exposed in cliff bands. Now, it is the breakdown of these softer sedimentary and also volcanic rocks that produces soils that are fertile enough to support the rich meadows that make Garibaldi famous. If this whole Garibaldi landscape was granite, I would guess that the amount of meadowland would be vastly reduced, because granite just doesn't break down quickly to form the fine particles that therefore become sort of the soil, the mineral soil, and release nutrients. It's really, in a sense, you might say that the sedimentary rock and the volcanic rock are sort of the alpine meadow heroes. They are a requirement to some extent to produce this abundance of high meadow. Okay, well, maybe it's time to get to the main act here, which is Garibaldi's volcanoes. And so the question, of course, is, well, okay, where are they out there? Show your face. And right across the lake, we're looking at a cluster of volcanoes, almost like a cascade of them. Off in the far distance to the left is Mount Garibaldi volcano. That's the mother volcano of them all. And then other smaller volcanoes. One, the Table, that curious flat-topped one. I'll come back and talk a bit about that. And then immediately across the lake is Mount Price volcano, which really has quite a conical look to it. When you realize it's a volcano, you go, okay, I know, I get that. And then it has two subsidiary satellite cones adjacent to it. And the one to the west is called Clinker Peak Volcano. And I'll come back to that too, because it becomes an important part of the story yet to come. If we pivot 180 degrees and look to the north, what we see are more volcanoes. There's Black Tusk, very famous. There's Cinder Cone, which from this point of view doesn't so much look like a volcano. From other points of view, it's much more conical in shape. And then let's not forget a lava flow that has come off the Cinder Cone, and the trail down to Helm Creek crosses right across that lava flow. So we are in the midst of a field of volcanoes standing here on Panorama Ridge. And here's a view of the whole volcanic field Now we're up above Squamish, maybe more like the Stawamus Chief. We're high in the sky and we're looking north toward Whistler, and we're looking across Mount Garibaldi, and Garibaldi Lake is further in the background. And what you can see is just a whole bunch of small volcanoes and big Mount Garibaldi volcano and lava flows. And the one in the foreground, which is the biggest of all the lava flows, Ring Creek lava flow, flowed almost all the way to what is now the town site of Squamish. Um, anyways, this is the Garibaldi volcanic field, and collectively, these volcanoes that number at least 12 have been active pretty much over the last 1.3 million years. The last eruption being about 9,000 years ago. So fortunately for us, we get the volcanoes, but we haven't had any volcanic activity for 9,000 years, which is good news. So what I'd like to do now is sort of poke into two volcano stories, just to sort of illustrate some of the diversity and variety of Garibaldi geology. Garibaldi is famous, and Mount Cayley nearby has a cluster of volcanoes, small volcanoes attached to it, which are also part of this famous aspect, and that is there are a whole bunch of these eruptions that occurred during the Ice Age, and none makes that story of fire meets ice more sort of palatable than the Table. So let's focus on the Table. Very odd mountain, very odd for the obvious reason that, holy Moses, it's got a dead flat top in a landscape where there's nothing else that's even close to having a flat top. The peaks around it are all craggy and ragged. And the Table was one of the first problems that Bill Matthews took on when he sort of came to the Garibaldi country. It was just such a confounding feature. He determined that it appeared to have horizontal layers of lava making it. But that was a huge puzzle because lava should flow laterally for large distances. Yet he could find no other evidence of these lava flows anywhere in the area. They seem to be tightly confined to a small space. And the sort of the kernel of the explanation came to him by his knowledge of Iceland and the fact that there were and are to this day volcanic eruptions happening through the glacier ice fields. And we can't see what's going on down there, but something curious is happening. However, in Garibaldi, the ice is gone and the story is revealed. What Bill interpreted was that, during the Ice Age, there was a volcanic eruption under the ice, forming sort of a short lava flow that couldn't go far because it immediately chilled against the glacier ice that surrounded it. And over time, successive eruptions built up essentially a stack of pancakes of lava flows within and then finally breaching the surface of the glacier, so that essentially a lava lake would have been exposed at the surface. And when the ice melted away, we are left with this odd flat-topped mountain. And that is a sort of one snapshot of a sort of an odd geologic feature. Now I'd like to return to Garibaldi Lake, which I've already pointed out is a very odd lake. And, odd's always an interesting thing, because what does the word odd mean? Odd basically, piques your curiosity. You go, okay, I'm not getting this. This isn't usual. So usual processes might not be able to be invoked to explain it. So we've got this very high altitude lake that's very deep. And Bill Matthews threw his mind to this. as well. And what he decided was the explanation was that Garibaldi Lake started its life as an empty stream valley. And this was during the end of the last ice age when, and I haven't shown it here, but the Cheakamus Valley, which is way over in that sort of hazy valley to on the left or on the right side of the screen, off to the west, would have been filled still by a valley glacier. But this part of the uplands, the ice had melted back. It was thinner in the first place, and it melted back first. It was still hanging around where it was thickest in the valleys, and so there is this sort of proto Rubble Creek that is flowing down the valley and draining out onto the glacier. And then all hell breaks loose. Clinker Peak erupts, and a big lava flow descends down into the valley. And the most interesting thing about this lava flow is that it becomes very, very thick. And it becomes thick because it can't do what it would have done had there been no ice age, and that is flow down into the Cheakamus Valley, down Rubble Creek and into the Cheakamus Valley. It can't because it's filled with glacier ice, and the glacier essentially, or the lava freezes against that surface. And so a huge thickness of lava builds up over 300 meters. It blocks the lake. The lake waters rise, and the lake waters rise till they can spill around the edge of the glacier, around the edge of the lava flow. And so just finishing up here, let's leave Panorama Ridge, and we'll go and take a look from space down at the barrier area over on the left or on the right side of the screen. And here we're up in space. We're looking down at the barrier that we stopped at the barrier viewpoint to get a close look, and then continued up the trail to Garibaldi Lake. And if we sort of look behind the barrier, what we see is a lava flow. And the lava flow, interestingly, has these sort of raised edges, these levees that mark its edges that sort of run all the way back to Clinker Peak, the source of the lava flow. And during the eruption, we had lava coming down the main flow, but also spilling over these lobes that extended into what is now Garibaldi Lake, formed the campground lava flow, and also ran into glacier ice at the barrier. And that is the end of the lava flow. It basically was chilled at the glacier, and then when the glacier melted away, this huge lava face was left, which later collapsed in at least 2 landslides. And to summarize, if we were looking in cross section now at starting the oldest at the top, going down, we'd have, remember, Rubble Creek just sort of flowing down onto the glacier, and then the lava flows from Clinker Peak, blocks Rubble Creek. The lake is formed, but it is stalled up against the edge of the glacier, creating this steep lava face. And then the ice retreats, melts away, and that vertical face collapses at least twice, most recently in the 1856 landslide. And with that, I'm calling it a wrap. And what I'd like to do is go to your questions. So I'm looking forward to a good conversation.
That was fantastic, Bob.
Well, thank you.
I see there's some good questions here coming in on the chat line. A couple of them are, with glacial retreat, which is accelerating, what other consequences are you most concerned about, and how might Garibaldi address these through park management?
Well, great question. Uh, I mean, the ice as it retreats, more and more ground becomes open. All of it is revegetating. I don't know that it creates any sort of acute management issues. It may specifically for particular ice fields where access has not been possible and now is. It may, uh, any slope which has essentially been stabilized against ice and loses ice has the potential, not necessarily, but has the potential um, to fail, at least in a small way. So some of these steep faces may be more prone to rockfall. It certainly has consequences for mountaineers and climbers who have used the glaciers as highways, not so much in the summer when they're heavily crevassed, but in the spring when there's still, good snow bridges intact. But with the loss of those, in many ways, fast paths, the crossing, rocky terrain is just a much slower process. So access will be affected in some cases for sure. But nothing jumps to mind. But it's a good question, and I really have never put my mind to that question. I'll think about it.
I'm just going to jump in here and add something to what Bob said, but I'll also just first let everyone know that you're all on. You can unmute yourself now if you want to ask your question out loud. But I was just going to say that if people are accessing those rocky areas and they happen to have some seeds on their boots, they could be actually bringing in invasive species. So that is something to think about when you're going up to these high terrain areas. It is good to clean your boots.
And Dorothy was wondering, with the melting of glaciers, would there be more volcanoes erupting?
Well, you're bringing, Dorothy, a very interesting point. One of the features of Garibaldi volcanoes and Mount Cayley, which is across the valley, is that they were very active during the Ice Age. And at the end of the Ice Age, they've shut down. The glaciers left, the volcanoes stopped erupting. And there is a view held by a lot of geologists that believe that the Ice Age and the weight of the glaciers and the way that glacier ice would have sort of pressed down on the earth in places unevenly, perhaps triggering faulting. Um, that faulting may have allowed volcanoes to erupt because every volcano is essentially connected by a conduit to a magma source, and you need a conduit. And faults are often, or usually, the pathway for melted rock to come to the surface. And so, to your question, it might be exactly the reverse with the glaciers receding and no particular differential loading happening. There may be less likelihood of volcanic eruptions, but that's completely a speculation.
Um, and Joan was asking, oh my goodness, they're coming in quickly here, about where the Helm Glacier retreated. Would that eventually become a subalpine meadow?
It absolutely would be. And
Yay.
yeah, no, it's though it won't happen fast. In that, well, I shouldn't say that. I'm not a biologist, and in fact, I will take that whole statement back. Yes, I mean, that's where they're going. A life will pioneer as life will pioneer. And so, yes, there will be an expansion of the meadowlands. as not only, are trees and meadows sort of climbing in elevation, but they're advancing into these previously glaciated areas. And we know that the glaciers basically plowed over and destroyed various subalpine forests, um, because it's that woody material that dates these moraine ridges that I was talking about in the Sphinx Valley. And so that same woody debris, evident of at least subalpine forest in places, occurs in most of the recently deglaciated areas. So yes, we'll have more alpine meadows. The one caveat on that is, as long as the meadows advance faster than the forest that are advancing behind them do, that's always sort of a game. But clearly, there's a lot of ground now for the alpine meadows to advance into.
One of the other questions was from Murray, and I actually do remember all of this hullabaloo that was made too about whether there was a high risk of collapse on Highway 99, and I think they were completely closing one of the accesses to Garibaldi Lake.
Okay, I'm not familiar with that. Was it the Rubble Creek parking lot that they were concerned about? That would be the more likely one, but
I
I'm
think it might have been.
okay. Yeah, I'm not familiar with a particular closure, but if there was a closure, the let me backtrack a bit. BC Hydro monitors the barrier and the adjacent areas quite closely. They're very attentive to landslide hazard risk from that area. They have the Daisy Lake Dam facility, which was in the path of the last landslide, and so they pay a lot of attention to that area. Um, but with regards a particular closure related to a particular landslide risk, I'm not familiar in the recent past. Now, let me just back up. Back in the 1970s, there was a whole subdivision that was built on the sort of the landslide debris, and it had been permitted. A first phase of the subdivision had been permitted by the approving officer and built. And then when they went ahead with the second phase of the subdivision, the approving officer had heard some concerns expressed by geoscientists that the barrier was unstable and that the subdivision shouldn't be permitted. Anyways, the developer and the province went to court over this, and there was basically a settlement where, in the end, the judge agreed there was too much of a risk over the lifetime of the settlement, which would be hundreds of years, and so they moved that whole settlement north up to halfway to Whistler, and anyways, those lands were expropriated. The owners were given different lands, and so that was one of the biggest pieces of resettlement and expropriation ever conducted in British Columbia because of a geological hazard. So that happened in the 1970s, and Dr. Bill Matthews was part of the technical team that essentially were expert witnesses in that court case.
And yes, Murray says that was Rubble Creek he was talking about, and he remembers all the hullabaloo about the subdivision too. So you've got the timing just right there. Is it correct that the last ice age was caused by a period of active volcanoes all around the world, causing particulate blocking of the sun? That's a question from Rosemary.
I think what Rosemary is speaking to is this period of time called the Little Ice Age. And that's this most recent period of ice advance from 1300 to 1850. And I think the cause of the Little Ice Age is somewhat speculative, still among scientists. It only affected uh, North America and Europe. It didn't affect the whole globe. So it has something to do with the North Atlantic and circulation in the North Atlantic. But it also appears to coincide with a series of major volcanic eruptions that were essentially built on top of other stressors, so that you're absolutely right. A big volcanic eruption can put essentially aerosol material into the atmosphere that reflects back sunlight and causes cooling. And if it's a big enough eruption, global cooling. And so those eruptions, and I'm thinking of a series of big eruptions, including Tambora in the 16, 17, 1800s, were certainly part of the ingredients of creating the conditions for the Little Ice Age, which is this most recent period. That's something completely separate from what we generally refer to as the Ice Age, which ended 11,500 years ago.
I'm going to jump in here with a question from Uwe Zimmerman. During the last ice age, were all the mountain caps covered in ice, or was it possible, or is it possible to tell which ones might have been looking out at the glaciers?
Okay, let me just jump ahead to something. I'm not sure if I've got the slide I can. Oh boy. Okay, no, let me just sorry.
You've
I
got
thought,
lots more slides there.
yeah, no, I should have looked a little more carefully for where I was going. Uh no, I unfortunately don't have it. Anyways, let me just go back to where I was. Um okay. Um yes, you can. Um yes, you can tell how high the ice was, and I thought I had an illustration here that would show that. But essentially, during the peak ice age, only the very tips of the highest peaks in the Vancouver area stood above the ice, and you can stand at a place where you can see these craggy peaks and actually figure out how high the Ice Age glaciers went, because the highest peaks are craggy, but just below that, the ridges become softened and rounded, and the lowest landscape elements, the hills and the low mountains, are very rounded. And what that is telling you is that the glacier ice um, was thickest over the lowest features and ground them the smoothest, and the mid elevation features, and now we're talking, oh, say 1.5 kilometers high, were somewhat rounded. And then above about 2 kilometers, craggy peaks poke up. And you can see those from Horseshoe Bay. That was the image I was going to show you, where you're looking north up the sound and you can see the high peaks of the Tantalus, craggy peaks. Those were above the ice. But everything else in Howe Sound, viewscape that you're looking at, was overrun by ice. And the thing in the foreground, which is Boyer Island, which is a beautifully smooth landscape, but is very low elevation, was extremely rounded. So it's a game you can play when you go into the mountains, and you can sort of see the height of glacier ice in the mountains around you, just by looking for the high craggy peaks, and then drop your eye down until the craggy peaks stop happening and you get into sort of rounded summits, and you're looking right there at the top of the Ice Age glacier when it was at its maximum.
Jim has a nice long question here, and I'm not quite sure I completely understand it, but I'll try. Regarding the formation of Garibaldi Lake, if Highway 99 area was covered by a glacier, wouldn't the area now occupied by Garibaldi Lake also be glaciated since it is at a higher elevation? And so it would seem there should have been no Rubble Creek to be dammed.
No, I like Jim's question.
Oh,
And
good.
yeah, no, I like Jim's question, and it's a question I've had to ponder myself. But the way that Bill Matthews explained it and it comes to my understanding is, and it's counterintuitive. Um, the During the end of an ice age, deglaciation, um, at the scale of an ice age, the first lands to sort of appear out of the ice are the high elevation uh, areas because that's where the ice is thinnest. And and the last place that the ice persists is in the valleys where it's thickest. In the Cheakamus Valley, the ice was probably 2 kilometers thick, but over, Garibaldi Lake, it was probably more like maybe a kilometer thick. And in the uplands around it, there would be even thinner, maybe just 100 meters or less. But back to Jim's question, you're saying, well, wouldn't the ice have sort of hung out in the valley that Garibaldi Lake now fills? And I agree. I would think, yeah, that would make sense. But here's the evidence that we can sort of attack that question with is sort of submerged. We don't know, we can't sort of see the lake floor to get more information, but there has been, and Steve Quain is working on this. Steve used to teach at Quest University, and he now is a proponent for this new fire and ice geo region that is really promoting geological storytelling all through the sea to sky corridor. Anyways, Steve has been doing imaging of the lake floor using sort of sonar type equipment, and looks at the shape of the ice of the lava flow in underwater as we can see it as far as the lake level, and then we lose sight of it. But his sonar work has sort of detailed the shape of it as it heads down deep into the lake. And there's no evidence, interestingly, that lava, as it flowed, was impeded by anything. If there had been ice there, it probably would have formed another vertical wall, like the barrier, against which it froze. But it doesn't. It just seems to sort of go down and down and down and down, suggesting there was no ice in the lake at the time. Anyways, that's the only piece of evidence that seems to speak to Jim's question, but it's a great question. That was sort of a real puzzle to me, and I mean, it remains a puzzle, and you just go, that's something that Steve will be able to speak to more clearly as his research continues.
Thank
But
you, Bob. I
but
noticed
I
one of
like
the
that. I like that. Jim, you're
good.
paying attention.
Well, one of our guests says we could be here till 10 p.m. Woohoo! This is so interesting.
Oh, good.
And one of the others said, I guess the lions might be an example of that too.
The craggy sticking up.
Yeah.
Yeah, the lions are right on the threshold because they're
Aha.
they're somewhat rounded at the top.
That's true.
Yeah,
That's
so they were craggy, but they just had a bit of ice scouring them slightly. So they're close to right at that high water mark of the Ice Age glaciers.
Aha. And one of our last questions was actually one of the first ones, but there were two parts, so I didn't get to the second part before. And that was, would you consider doing a field trip up to the Garibaldi Lake area sometime for Nature Vancouver? Or are there some being led up there?
That's a great question. I don't know of any, but that would be the sort of thing where, if we could get a couple of geologists together, that would be sort of a fun exercise of doing this. So, um, yeah, I'd be open to it. Um, uh, the trick would be that all of this conversation is pretty slow, and so it'd have to be based out of a campground. The
Yes.
trick there is you got to book in advance, so there'd have to be, a fairly high level of organization. I don't know, maybe Nature Vancouver is up for that type of organizational work, but you'd need to be based out of the campsite, and then be able to poke for a day or two in sort of these different places looking at the geologic stories.
Yes, I'm going to have to go back into the history archives of Nature Vancouver because, like I said, I think I first went up there much earlier in my life, and I think it was a Nature Vancouver outing. And I think we did stay up there because we did Panorama Ridge and we did a whole bunch of these different places.
Well, there were camps up there.
Yes.
A number of years there was camps.
Okay.
There's actually one other question to Donna, and it's Gail.
Okay. I'm sorry I missed that.
Yeah, your thoughts on the stability of sediments under the present day Helm Glacier.
Um, the sediments underneath it, the Helm Glacier in general is a fairly low sloping glacier at present, and the snout is at the last time I saw it is still sort of right the little pocket lake right there. The glacier snout breaks into the lake. I don't know of any issues with the stability of the sediments underneath the glacier. You never know, and it would vary from time to time. There could be sort of an ice wall that collapsed and put up a wave in that small lake, and if you happen to be on the far shore at the time, you might get drenched
Mhm.
with a sort of a wave. That would be sort of the only hazard that immediately comes to mind. Other than, actually, this is a good question. Fresh moraine left by a glacier that's just melted out is extremely loose, and essentially unstable. It can be like some of the places I least like walking are recent moraine ridges because the stuff's all in motion. It's just been dropped by the glaciers. It really hasn't sort of, if it's quite recent, it hasn't settled in, and it's yet to sort of find its equilibrium. And so it's crummy stuff to walk on, and it's dangerous if you're walking in a couple people and you can sort of set stuff in motion on people below you. So, that type of issue certainly is important and is a sort of a stability issue for people walking on it or walking behind someone who's higher up on the ridge. So that would be the one thing that does come to mind.
I want to just jump in and say, were you ever a teacher or a professor teaching students? Because, oh my gosh, those students were very lucky.
Hmm.
No, my wife's a teacher.
Okay.
Yeah, she's a faculty at Stanford, and so she's the one in front of the class all the time. But I've always had fun um, talking about this stuff, particularly geology, and um, yeah. So I've led lots of field trips and talked to lots of school groups and stuff, and that's sort of how I have done my teaching. But I love it, and particularly, I when I was in grad school, in grad school it can be a bit of a nervous affair. You're trying to sort yourself out, and you're surrounded by a lot of sharp people. And I always remember one of the older gentlemen, faculty members, saying to me, he said, there's no such thing as a stupid question. It doesn't even cross
Yeah.
my mind. He said, I so enjoy just sort of understanding where people are coming from. And the wonderful thing about a question is that it's the start of a conversation. And so questions always drive the most interesting part of any sort of presentation that I do, because it's then now we're talking, you know. Before that, I'm just blabbing. And who knows whether it's over your head or below your feet or where it's going. But once we're in a conversation, then there's, we're talking to each other, and that's fun.
So it's not just blabbing, because you have so many people here in the chat saying, what a fascinating presentation.
Oh,
Yes.
Thank you
good.
so much, Bob.
I'm
Well,
going to also actually read one of the comments that came in from Bengal, and she says, "Thank you for walking with us around Garibaldi Lake in geological time stories of the surrounding mountains in a virtual meeting, Bob." I couldn't say it better myself.
oh, lovely. Well, that is the lovely thing about sort of pictures, and you can literally take a virtual trip and go take a look at what's going on.